So today we will revise chapter 6 and also then we will do chapter 7 because we have finished reading both of them. Till chapter 5, which was a big topic, was for transaction and concurrency control. Coming to chapter 6, B tree variants. So basically we have studied the classical B tree with these nodes, typically the non-leaf nodes in B plus trees. They just have these pointers, uh, which are the keys, and the leaf nodes, they have the key values. And we talked about the representation of a node as, say, a slotted page, etc. So all that was good, which allowed laying out the data so that when we have to look up a particular key, we will be able to find it with a minimum amount of disk access. But still, like, there were a few disk access. Some pages may be already put in the buffer management. We talked about buffer management also, pinning and whatnot. So all that was there. And then with regard to writes, well, we have seen that B tree writes are not really great. They may keep some space for keys, like their fill factor may be, say 50-60%. If more insertions are happening in a particular node, then there will be splits. If goes underflow, then there will be mergers, etc. All these will require things to be again changed on the disk. So what can be done to optimize the situation further? So there are variety of these B tree variants. Let's look at them. First one, copy on write. Okay, so copy on write, some new write has come in. What we are going to do is create new nodes, basically containing the writes, and it will essentially become like a new tree. Whatever path which we have changed will be newly constructed, and then there will be pointers from this new tree to the nodes of the earlier tree, and writes are going to go there. Eventually, whatever reads are happening on the old one, they will be there, and then they'll go away. They'll migrate to the new version of the tree. So they are saying that biggest advantage of this approach is that readers require no synchronization because written pages are immutable and can be accessed without additional latching. Yeah. Readers do not block writes. Pages system crash cannot leave pages in a corrupted state. Since the topmost pointer is switched only when all page modifications are done. Yeah, so this is a nice diagram of a copy and write B tree. One of the storage engines using copy and write is the Lightning Memory Map database at OpenLDAP. So OpenLDAP, so LMDB holds only two versions of the root node, the latest version and the one where new changes are going to be committed. Fine. Next section, abstracting node updates. So this is talking a little bit about languages like C, C++, where the raw binary data stored in B-tree nodes can be reinterpreted and native pointers can be used to manipulate it. Fine. And then in some languages like let's say Java, etc., we have representation, which is languages representation, and then yeah. Alternatively, B-tree nodes can be materialized into objects or structures native to the language. Blah blah blah. And then there is so this approach has higher memory overhead. What is the third approach? So third approach is provide access to the buffer backing the node. Okay, so some of this is like something they've talked about, but I don't really see the strong value of this. Let's go to the next B-tree variant, which is wired tiger, lazy B-trees. So lazy B-trees, basically they have a update buffer. Okay, updates are saved into the update buffer. So here is a nice diagram. We can see an update buffer. So there has to be your wall, right? I think, okay, they did not really talk about so update buffers are accessed during reads, blah blah blah. When the page is flushed, update buffer contents are reconciled with page contents and persisted on disk. Update buffers are implemented using skip lists. So skip lists, essentially they are a tree-like structure. They allow us to do logarithmic searching. They organize data into levels, lists with levels. Both clean and dirty pages in WireTiger have an in-memory version and the reference a base image on disk. Fine. This WireTiger guy did not talk about if you're just updating update buffer, how is the update buffer actually maintained? It is implemented using skip list, but that would be only in memory, right? What about things if there is a crash? I think wall has to be there. Fine, they didn't talk about it. It has to be there. Then lazy adaptive tree. Okay, lazy adaptive tree is here. Lazy adaptive tree messes around with the same idea, although rather than per page buffer, now there is a buffer for like a part of the tree. And then these buffers are also in some hierarchy. Lazy adaptive. Fine. Now FD trees. FD trees are very similar to LSM trees. I couldn't really figure out why, what is the difference. So it has a small mutable tree head and multiple immutable sorted runs. These sorted runs are like SS tables. This approach limits the surface area where random IO is required to the head tree, small b tree, buffering the updates. As soon as the tree fills up, then we transfer it to the immutable run. And then if the size of the newly written run exceeds the threshold, its contents are merged with the next level, etc. So now there are a lot of these run files. So there are some techniques here, how to deal with a lot of these, how to, you will have like read amplification, because you have to read, so you may have to read through a lot of these run files. What do you do? So you have to like normally put indexes and whatnot, right? And you have to do compaction, all of this you have to do. Stuff mentioned here, this fractional cascading. Okay, so what is happening in fractional cascading? We have three multiple sorted arrays. So A1, A2, A3, what we have done is we have taken, so A3 had 16 and 30. Now we have taken 16 and 30, we have put them in A2 also. We have pulled elements into A2, and then A2, from A2 also 25, 30 are now in A1. Okay. So this allows creating some sort of bridges or fences, as the FD tree paper calls them. It allows like efficient pruning. The second thing is logarithmic runs. Creating logarithmically sized sorted runs. Factor of k, created by merging the previous level with the current level. So the initial levels will be smaller, and then the deeper levels will be bigger. And then there has to be like tombstones also. All of this where there are compactions and multiple SS tables or these run files, etc. The data is scattered. When you delete, what do? You need to insert a tombstone, and you can't remove the tombstone that easily, because if you delete it, the resurrection can happen from a previous SS table or a deeper run. So you have to wait till like you do compaction all the way down or down levels, etc. So that is FD tree at a very high level, similar to SS tables. Now comes BW tree. So BW tree, or a buzzword tree, we can batch updates to different nodes by using append only storage, link nodes together into chains, and use an in-memory data structure that allows installing pointers between nodes with a single compare and swap operation, making the tree lock free, blah blah blah. So here's a diagram of a BW tree. So we can see that there is a base node, and then there are these deltas, right? Chains. Fine. This looks lot similar to like buffers, update buffer. Modifications form a chain link list with the newest update, blah blah blah. Since the size of base and delta nodes are unlikely to be page aligned, it makes sense to store them contiguously, having a node as a logical rather than a physical entity. Okay. To update a BW tree node, the target leaf node is located by traversing the tree from root to leaf. Now there's a mapping table. Mapping table contains virtual links to the target base node or the latest delta node in the update chain. Fine. The new delta node is created with a pointer to the base node or to the latest delta, and the mapping table is updated with a pointer to the new delta node created during step 2. An update operation during step 3 can be done using CAS, which is an atomic operation, so all reads concurrent to the pointer updates are ordered either before or after the write. Fine. Structural modification operations. Talking about split, parent, update. Okay. Split. A special split delta node is appended to the splitting node to notify the readers about the ongoing split. Okay. So it's more algorithmic like tricks here to deal with this BW tree, how to handle splits and merges, and then delta chains can get arbitrarily long, so there is consolidation and garbage collection. Okay. Fine. Then there is cache oblivious B trees, but they are not found in practice. So, and then the summary. So these are some of the B tree variants.